This is the commentary for the chapter 7-8, version 2, organic chemistry, carbohydrates, lipids chapters. Let's go ahead and begin. So in this case right here, we're actually looking at biomolecules. So this is really going to focus on the biochem section. In biochemistry, because we're dealing with one type of molecule that an organism may prefer, then every one of these biomolecules has a very unique name. So unlike the systematic naming process in traditional organic chemistry, biochemistry, everyone has their own unique name. Before we get into the nitty-gritty details, for most of the biochemistry, you have to do a lot of memorization. So the key on this is to memorize. My teacher used to say biochemerization. Why it stuck with me, I have no idea. But you have to memorize, memorize, memorize. Now, in this picture right here, we have a picture of a ribose molecule. This is the Fischer projection, which I am circling. Yes, you have to memorize this structure. Right next to it, we actually call this cyclic structure that it forms the Hayworth structure. Hayworth. And yes, you have to memorize the closed structure for this as well, or the cyclic structure. Both of these are considered ribose. If you go over to the other side, we have deoxyribose, and this is the Fischer projection, which I am circling in red, and this is the Hayworth structure, also known as the Hayworth cyclic structure. These are, as far as testing goes, these are fairly straightforward. I will literally say, okay, sketch me the alpha D ribose Fischer open chain, and then you'll have to draw this atom by atom just exactly as I have here. Or I could say something like this. I could say sketch the Hayworth cyclic structure, and you'd have to draw this right here if I asked for the cyclic structure for ribose. So, careful, make sure to make flashcards on this and do a lot of practicing. Practice, practice, practice. So you have to know these monosaccharides inside and out, both the open chain Fischer, which I'm highlighting in yellow, and the Hayworth cyclic structure. You have to know both forms. So I'm just going to move ahead a bit. And as I said over here, same thing. Glucose, memorize the open chain Fischer projection, and then memorize the Hayworth cyclic structure that you see right next to it. Galactose, same thing. Memorize, memorize, memorize. So memorize the open chain Fischer projection and the closed Hayworth structure. The Hayworth cyclic structure. Fructose, you get the idea. Memorize, memorize. This goes into important details about the Hayworth structure, and I'll go back to that in a second. This picture right here shows the open chain monosaccharide of glucose, and basically it's its tail is double backing on itself, so that way it can undergo a cyclic hemiacetal reaction. Hey, we studied these in the previous section. Now we actually get to apply them in real-world scenarios, such as in biochemistry. And this happens all the time. So just if you want to see a picture of this right here, and here we formed two possible cyclic structures, heterocyclic structures, if we want to be more specific, since there is an oxygen that makes up the cyclic structure. So technically it's heterocyclic. But I'm going to keep moving forward a bit. And here are various molecules you need to, guess what? Memorize. So memorize this structure right here, glucose 6-phosphate, and then memorize the structure right here. We call this methyl alpha D glucopyranoside. If these are monosaccharides, mono E mono, then when we combine them in a ether reaction, we create disaccharides. So this is an example of a disaccharide. And I'll let you finish writing that word right there because I'm just too lazy. Disaccharide. And I'm shooting through this really quick. Why? Because I can get to this slide right here. Memorize, memorize, memorize. Now when you have the first two slides memorized, for glucose, galactose, fructose, then these will actually be a lot easier, because the disaccharides are actually made up of the monosaccharides you memorized earlier. For example, maltose is made up of 2 glucoses, and if you memorize the individual Hayward structures, then you'll have no problem with the disaccharides. And we'll get into those in a bit. Here we have polysaccharides. Now, these chains can go on thousands and thousands of units long. So this is actually just a piece of the very long chain. So think of this as a polymer of monosaccharide sugar units, hence we call this a polysaccharide. We have different types of polysaccharides. In this case, here we have 2 types of starch. We have the unbranched version of starch, which is actually amylose. And then we have the branched version of starch, which is amylopectin. Yes, you have to memorize. Memorize, memorize, memorize. This is glycogen, animal starch. Basically, it looks like amylopectin. But if I ask you to draw glycogen, just draw me a snippet that, like you see here, and it's essentially amylopectin. Technically, glycogen's a lot more branched, but you really can't appreciate it in the pictures. I will, however, know the difference when you sketch it. So as long as you have the proper branch, it won't be an issue. Now, going back to the next one you have to memorize cellulose. Again, I'll be teaching you the patterns. If you've memorized the monosaccharide unit, then making the polysaccharide will actually be pretty easy. And I'll show you the differences between this and the various forms of starch. So, we're only going up to sugars in this commentary. The rest is fats. But right now, let's go ahead and go back to the very beginning. Notice for all these different pictures, from slide 3 to 12, they all focus on slide 1 and 2 as their starting unit. So we have to memorize these structures inside and out, and then the rest of the carbohydrate slides will be a lot easier for you to memorize and actually apply. So let's go ahead and go to this one right here. Let me go ahead and show you the tricks and how to memorize it, and I'll show you some key attributes of it to make it a little bit easier for you. So let's go ahead and focus on this one right here. This right here is the open chain ribose. Here you see the carbons. Technically, you don't have to have the carbons in the Fischer projection. It's up to you whether you choose to keep these carbons in there or not. What you absolutely have to have when you're drawing this is you have to make sure the alcohols are on the proper side. Keep in mind the Fischer projection is actually a summary of the wedge dash structures. So if you go back, we talked about sketching from wedge dash to Fischer projection. So you want to keep in mind that each of these hydroxyl positions, each of these alcohol positions are on a specific side, and they're meant to stay that way. You need to keep them in the right position. If I were to sit there and draw the hydroxyl on the left-hand side like OH, then it's completely wrong, and you would lose all of your points for that particular problem. Why am I being so picky on which side this alcohol is in? Well, keep in mind these are stereoisomers, and each one of these is a chiral carbon. By changing the position of this hydroxyl group to the other side, it's going to change the overall spatial arrangement. And when it comes to biochemistry, that's really bad. It turns out all of your enzymes for speeding up reactions in your body, they're tailored to only work with one type of biomolecule. And everything has to be perfect. Not only does it have to have the same, obviously, number of atoms and same atom type, it also has to have the same connections, and it also has to have the same 3D spatial arrangement. So if I were to sit there and change the arrangement of one of these carbons, automatically the enzyme wouldn't be able to read it and catalyze the reaction. And then it wouldn't work. So the body needs the proper type of molecule. It needs the proper type of isomer with the proper type of spatial orientation. I can't say that enough. Now, if you continue to take a look at ribose, it turns out that these open chain Fischer projection molecules, they love to undergo cyclic hemiacetal reactions. Now, we studied this in the organic chemistry portion in order to make our cyclic hemiacetals or cyclic hemiketals. And again, this does occur in your cell. Basically, these open chains are actually very easy for the body to break down for energy. However, there are times when the body doesn't want to break it down for energy, it wants to store it. So, in this case over here, this heterocyclic form of the sugar is used to store the sugar molecule to be used for energy at a later time. Now, it's this hydroxyl group which is going to go ahead and bend around and do a cyclic hemiacetal reaction on this particular aldehyde. The aldehyde is going to go ahead and become an alcohol, which I'm circling here. And the alcohol itself is going to go ahead and become the ether, which I'm going to go ahead and highlight with my pen. When it forms this brand new cyclic or heterocyclic structure, the spatial arrangement of each one of these hydroxyl groups is maintained. So the chiral carbons for each of these are maintained, and the arrangement of each of the hydroxyl groups are maintained. So in this case, this hydroxyl group is maintained, and so is this one down here. Consequently, if you were to sit there and sketch one of these hydroxyl groups, and you were to sketch it in a up position, then you've changed the chirality of that particular carbon. And when the alcohol is facing up, the new spatial arrangement, again, the body wouldn't be able to recognize that molecule, much less do anything with it. So, consequently, it needs to be written exactly like this with proper hydroxyl orientation, or it's wrong. Now, to help you appreciate the orientation of these alcohols and to give you a couple shortcuts on how to memorize this, let's go ahead and go to